Now let's look at factorial notation. A factorial is anything in the form of n factorial. So this symbol, the exclamation mark, signifies factorial, and n is an integer. So for n greater than or equal to 1, n factorial is the product of the first n positive integers. So we have n factorial. So it's going to be n into n minus 1 into n minus 2 into n minus 3 and so on into 3 into 2 into 1. Let's take a few examples. So 5 factorial will be 5 into 4 into 3 into 2 into 1, which is 120. Let's take 2 factorial. It's going to be 2 multiplied by 1, which is 2, and so on. So that's how this works. So an alternative recursive definition. Of factorial numbers is which can be extended to n factorial equals to n into n minus 1 into n minus 2 factorial. This is important, and so on. Using the factorial rule with n equals to 1, we have 1 factorial equals to 1 into 0 factorial. And therefore, for completeness, we define 0 factorial as 1. There's really no logic to it. We just define 0 factorial as 1 because it's convenient. First of all, we're going to get things like NCR, which we're going to learn soon. In this one, if R was 0, sorry, no, this. In this one, when we come across it, if we have something that is to the factorial of 0, we can't divide a number by 0. We don't know what it is. It's undefined. So therefore, for convenience sake, we define 0 factorial as 1. And now let's look at this point. It says n factorial equals to n into n minus 1. So therefore, what we can write 6 factorial as is 6 into 5 factorial. It's essentially the same thing. And 5 factorial can be written as 5 into 4 into 3 factorial. Or we can write 200 factorial would be 200 into 199 into 198 into 197 factorial. This is how it works. And now let's solve some questions. In these questions, you'll have to simplify the expression as much as possible. Okay, now let's look at the first question. We have 6 factorial divided by 5 factorial. We can write 6 factorial as 6 into 5 factorial divided by 5 factorial. We can cancel this out and we're left with 6. As you can see, this is very simple. And now let's look at a similar example. 6 factorial would be 6 into 5 into 4 factorial divided by 4 factorial. We can cancel this out and we're left with 30. And now this might seem complicated, but let's break it down. We can write n factorial as n into n minus 1 factorial plus n minus 1 factorial divided by n minus 1 factorial. We'll take n minus 1 factorial as common. So we're left with n minus 1 factorial into n plus 1. Then we divide this by n minus 1 factorial. This cancels out and we're left with n plus 1. Now let's simplify this. The top can be written as n plus 1 into n minus 1 factorial divided by n minus 1 factorial. Cancels out and we have n squared plus n. We can write 12 factorial as 12 into 11 factorial minus 2 into 11 factorial. Let's take 11 factorial as common. 11 factorial, 12 minus 2. This is going to be 11 factorial into 10. We can leave this in this form. And now let's do the same with this. You can write 9 factorial into 10 plus 1 divided by 11. This cancels out. We're left with 9 factorial. And we have the last set of questions. N plus 2 factorial can be written as n plus 2 into n plus 1 multiplied by n factorial divided by n factorial. Therefore, we have n squared plus 3n plus 2. Simple, right? Now let's solve this one. The lowest is this one. So we can take 6 factorial as common. So it's going to be 7 minus 1 plus 8 into 7. That's 6 factorial into this would be 6 plus 42. 6 factorial into 48. And now, yeah, no, that's all. This is all we can do with this. And so we're done with all of these questions. The next topic is the binomial coefficient. This is used for permutation and combinations. It's mainly used for combinations, not really for permutations. For permutations, we use NPR instead of NCR. But now let's just concentrate on what it is. So it's defined by brackets NR in the vector form. Or you can write this as NCR or CNR. So these are the three ways you can represent the binomial coefficient. And this is defined as n factorial divided by r factorial into n minus r factorial. This is something you'll have to remember, but there is this function on your calculator that you can use too. Either way, it's good to remember this because there are certain questions that do ask you to expand this, without like using the calculator. They will tell you to prove something in something, and therefore you'll have to know the expansion. So this is important. Just remember that it's n factorial divided by r factorial into n minus r factorial. Well, just think of this as n, and the bottom one, instead of multiplication, think that it's addition. So r and r get cancelled, left with n and n. That's how I remembered, but you can remember it however you want. Now let's work out an example. Let's do this one. Expand this. This is basically 5c2. It's going to be n factorial divided by r factorial into n minus r factorial. Here n is 5, r is 2. Therefore, this would be 5 factorial divided by 2 factorial into 5 minus 2 factorial. We can write 5 factorial divided by 2 factorial into 3 factorial. 5 would be 5 into 4 into 3 factorial divided by 2 factorial multiplied by 3 factorial. These get cancelled out. We can simplify this to 5 into 2, which is 10. This is the answer. And now let's do some more examples. Let's work out this one. Go ahead, give it a try. This is 4, by the way. Give it a try. This is going to be 4 factorial divided by 2 factorial into 2 factorial. It's going to be 4 into 3 divided by 2, which is 2 into 3, which is 6. That's the answer. And now let's look at one of the show questions. This is show that this is this. Okay, we know that NR is NCR. So it's going to be n factorial divided by r factorial into n minus r factorial. Let's do the same for this one. And multiplied by, this is going to be n minus of this, which is going to be n minus of minus r, which is plus. These get cancelled out. We're left with the same thing. This is one of the most important properties of the binomial coefficient. So when we're doing the combinations, you'll understand why. So I'll just try to explain this right now. You don't have to really know this right now. Once I explain permutation combinations, this will make a lot more sense. Imagine you have 5 boxes. So you want to choose 3 of these boxes. And how many ways can you do that? You can do this, 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 and so on, right? This is the same thing as leaving. So choosing 3 boxes is the same as leaving 2 boxes. So let's say we give the first 3 boxes, not the first, any 3 of the boxes to person A and 2 of the boxes to person B. So if we give 3 of the boxes to A, it's the same thing as saying we give 2 boxes to B. And so therefore we get 5C3, which means that you're choosing 3 artifacts or things out of the available 5 items, which is also the same as 5C2. That is why this is very important. So we know that 5C3 is 5C2. So choosing 3 from 5 things is the same as choosing 2 from 5. It's like choosing this, leaving this. That's the principle. I hope that's clear. Now let's solve the last question. It says find k if 9k is 4 into 7k minus 1. It's going to be 9 factorial divided by k factorial into 9 minus k factorial, which is 4 into 7 factorial divided by k minus 1 factorial multiplied by 7 minus k plus 1 factorial. We can expand this. 8 into 7 factorial divided by k into k minus 1 factorial. And this will be 9 minus k factorial. It's going to be k minus 1 factorial multiplied by 8 minus k factorial. We can cancel 7 factorial and 7 and this and this. And now we can write this as what's 9 into 8? Okay, let's just leave that. I don't know. K into, this is gonna be into 8 minus k factorial. It's going to be 4 into 1 divided by 8 minus k factorial. This gets cancelled and this gets cancelled, and we're left with 18 by k multiplied by 9 minus k is 1. We can write 18 is 9k minus k squared. So k squared minus 9k plus 18 is 0. Now let's calculate this. do not have my calculator with me right now, but I'll just try to work it out. This is 9. Oh, wait, never mind. K is just 3 or 6. You factorize it. So this is what we get.